All right, future chemists, welcome. If you're prepping for the Chemistry Olympiad, you know you've got to have your bonding theories down cold. Today, we are diving deep into one of the most powerful and, honestly, one of the coolest tools we have, molecular orbital theory. This thing is a total game changer. Let's get right into it. So, here's our roadmap. We're going to start with the absolute basics, like why do we even need this theory in the first place? Then we'll get our hands dirty building MO diagrams, first for molecules with two identical atoms, and then we'll see what happens when they're different. We'll even kick it up a notch and look at bigger organic systems before we wrap up by tackling some real-deal problems.
So you might be asking, wait, don't we already have Lewis structures and VSEPR theory? Why another model? Well, because those simpler models, they can't explain everything. The absolute core idea of MO theory, the thing you have to get, is that electrons don't just belong to one atom or one bond. Nope, they're delocalized, spread out over the entire molecule.
Let's start with a classic chemistry mystery. If you draw a Lewis structure for an oxygen molecule, O2, you get a nice double bond, and all the electrons are neatly paired up. Now, Chemistry 101 says paired electrons are repelled by magnetic fields. That's called diamagnetism. But if you actually pour liquid oxygen near a powerful magnet, it sticks, it's paramagnetic. What is going on? Our simple model is clearly missing something huge.
And this is where molecular orbital theory swoops in to save the day. It tells us to stop thinking about electrons as belonging to atom A or atom B. Instead, they belong to the molecule as a whole. They live in these things called molecular orbitals, which are kind of like atomic orbitals, but they stretch across the entire molecule. Okay, so how do we make these molecular orbitals? Well, we use something that sounds fancy but is actually pretty simple, the linear combination of atomic orbitals, or LCAO. Let's take the simplest possible molecule, the H2 plus ion. Each hydrogen atom brings a 1s atomic orbital, which is just a wave function, really. If those two waves add together, they interfere constructively. You get a big buildup of electron density right between the two positive nuclei. This acts like electron glue, holding the molecule together. It lowers the energy, makes things stable, and forms what we call a bonding orbital. We call it a sigma orbital because it's symmetrical all the way around the bond.
But what about the other side of the coin? What if the waves subtract from each other? Well, that's destructive interference. It literally cancels out the electron density between the nuclei. You get a nodal plane, a dead zone where there's zero chance of finding an electron. This shoves the nuclei apart, raises the energy of the whole system, and creates a high-energy, unstable, antibonding orbital.
This energy diagram really pulls it all together. You start with two atomic orbitals on the sides at the same energy level. When they combine, they split. One molecular orbital goes down in energy. That's our stable bonding orbital. The other goes up. That's our unstable antibonding one. And those little G and U letters, don't let them scare you. They just describe symmetry. G is for a Garad, which is German for even, and U is for ungarad, or odd. It's just a label.
Okay, we've got the basic idea down. Now let's level up and apply this to bigger atoms, specifically the homonuclear diatomics from period 2. We're talking molecules like nitrogen, oxygen, and fluorine. The game gets a little more complex here because these atoms don't just bring s orbitals to the party, they bring p orbitals too.
Building these diagrams is a pretty logical, step-by-step process. First, the 2s orbitals from each atom combine to make a sigma bonding and a sigma antibonding orbital. Done. Next, the 2p orbitals mix. The ones pointing at each other overlap head-on to make another set of sigma orbitals. The other 4, which are parallel, overlap side-on to form what we call pi orbitals. Once you've got all those, you just stack them up in order of energy.
Now, here is a huge point. Write this down because it trips a lot of people up. The energy order of those orbitals is not always the same. For lighter molecules, like N2, there's this thing called sp mixing that pushes the sigma orbital from the p's to a higher energy. But for heavier ones, like O2 and F2, that mixing effect is weaker and the sigma orbital drops back down. You absolutely have to remember that the order flips between N2 and O2. It is key.
All right, so we've built the machine. Now let's see what it can actually do. This is the real payoff, you guys. We can use these diagrams to predict tangible, measurable things about molecules. Their bond strength, their length, even their magnetic properties. This is where the magic happens. And the first, most powerful thing we can calculate is something called the bond order. The formula looks simple, and it is. It's just 1/2
times the number of electrons in bonding orbitals minus the number of electrons in antibonding orbitals. That number tells you, basically, if you have a single bond, a double bond, a triple bond. It's a direct measure of bond strength.
So let's put it to work. For N2, you pop in its 10 valence electrons, run the calculation, and you get a bond order of 3, a triple bond. All electrons are paired, so it's diamagnetic. Perfect. Now for O2, with 12 valence electrons, the last two have to go into separate antibonding pi orbitals. Hund's rule, remember? This gives a bond order of 2, a double bond, but with 2 unpaired electrons. For F2, we get a bond order of 1. And for Ni2, if you fill everything up, you get a bond order of 0, which basically means no bond. The molecule just falls apart, which is exactly right.
And there it is, the answer to our original mystery. MO theory is the only simple model that correctly shows O2 has 2 unpaired electrons. Those 2 little electrons are the culprits. They act like tiny little bar magnets, and that is precisely why liquid oxygen sticks to a magnetic field. It's just a beautiful confirmation of the whole theory. And look, bond order isn't just some abstract number we calculate for fun. It has real-world physical meaning. A higher bond order means a stronger bond and a shorter bond. Simple as that. The triple bond in N2 is way stronger and shorter than the double bond in O2, which is in turn stronger and shorter than the single bond in F2. The theory predicts the trend perfectly.
Okay, so far we've been dealing with identical twins, right? 2 nitrogens, 2 oxygens. But what happens when the atoms are different, like in carbon monoxide or hydrogen fluoride? Now things get even more interesting, because we have to deal with electronegativity. It all comes down to one word: electronegativity. In HF, fluorine is an electron hog, so its atomic orbitals start way lower on the energy ladder than hydrogens. The rule is that orbitals that are closer in energy interact more strongly. This means the resulting bonding MO is mostly fluorine-like, and the antibonding MO is mostly hydrogen-like.
And this, right here, is the quantum mechanical origin of polar bonds. In a molecule like N2, it's a perfectly matched tug-of-war for the electrons. But in HF, fluorine is winning that tug-of-war big time. The bonding electrons spend way more time around the fluorine, creating a partial negative charge there and a partial positive charge on the hydrogen. MO theory explains exactly why this happens.
Now you might think this is all just for tiny 2-atom molecules. Nope, we can scale this thinking up to understand some of the most important molecules in organic chemistry, those with conjugated pi systems, the ones with alternating single and double bonds. We use a little shortcut called the Huckel approximation.
The Huckel method is cool because it lets us ignore everything but the pi electrons. In ethene, 2 p orbitals make 2 pi MOs. In butadiene, 4 p orbitals make 4 pi MOs. You see the trend here, right? As the system gets bigger, the electrons can spread out, or delocalize, even more. And spreading out like that leads to extra stability. Butadiene is more stable than just having 2 separate double bonds.
And then we get to the king of them all, benzene. Its total pi energy is 8 beta. Now, if it were just 3 normal isolated double bonds, you'd expect an energy of 6 beta. That extra stabilization of 2 beta is what we call delocalization energy. It is a massive amount of extra stability, and it's the entire reason for benzene's legendary unreactivity, what we call aromaticity.
Okay, theory time is over. Let's get our hands dirty with some problems. This is how you really know if you've got this stuff down. Here are a couple of classics that really test your understanding of MO diagrams.
First up, you've got a nitrogen molecule, N2. You blast it with some energy, an electron flies off, and you're left with the N2 plus ion. Is that new bond stronger or weaker than the one you started with? The whole trick is to think about which electron you removed.
Let's think it through. In N2, the highest energy electron is in a bonding orbital. It's part of the glue. So if you remove it, you're taking away some of that glue. The bond order drops from a solid 3 down to 2.5. Less glue means a weaker bond. So the original N2 molecule is more stable and has a higher dissociation energy. Okay, next round. Same deal, but with fluorine this time. We take F2, zap it, and make F2+. Stronger or weaker? Go on. Take a second, check your MO diagram, and think about where that electron is coming from. This one's a bit of a trick question. In F2, the highest energy electrons are in antibonding orbitals. These are the bad guys, the ones actively trying to push the molecule apart. So, if you kick one of them out, you're actually helping. You're removing a destabilizing force. The bond order actually goes up from 1 to 1.5.
This makes the bond stronger and shorter. How cool is that? The F2+ ion is actually more stable than the neutral molecule. So what's the big takeaway here? Molecular orbital theory is, well, it's just incredibly powerful. It explains things that other theories can't even touch, from the magnetism of oxygen to the stability of benzene. But it's more than just an explanation tool. It's a blueprint for design. Once you understand this energy landscape, you can start to imagine building brand new molecules from scratch with exactly the properties you want. And that, right there, is the amazing future of chemistry.